Hi, I am Sharada Karthikeyan, and this is a presentation of the paper Influence Maximization on Temporal Networks, a review published in Applied Network Science in 2024 by Eric Yanchenko, Shioshi Murata, and Peter Holm. I chose this paper because it provides a comprehensive and insightful overview of how influence spreads across networks that evolve over time, which is a topic highly relevant in both social and information systems. Before we get started, let me briefly explain what influence maximization means. Influence maximization is the process of identifying a small set of most influential nodes in a network, which, once activated, can trigger the largest possible spread of information, behavior, or ideas through that network. In simpler terms, it's about finding who matters most in spreading influence efficiently across a system. Now, with that basic idea in mind, let's begin by understanding why this topic matters and what motivated the authors to study it. The motivation of this work comes from observing how influence spreads in real world systems, be it viral tweets, marketing campaigns, or the spread of diseases. Traditional influence maximization studies assume that networks are static, meaning that the connections never change. But in reality, relationships fluctuate. New people join, some people leave, connections strengthen or fade between people. To capture this dynamic behavior, we use what are called temporal networks, networks whose structures evolve over time. In temporal network, each edge or interaction is time stamped, so we can model how connections appear, disappear, or change as time progresses. Because of that, static models often give inaccurate predictions. So the authors emphasize the need for temporal models which can adapt to these evolving connections and capture real time dynamics. This motivation bridges theory and practice, helping design better interventions, targeted marketing, and even epidemic control strategies. Now that we understand the motivation, let's look at how this problem developed historically. To see where this paper fits, here's a short timeline of influence maximization researches. It began with Kemp in 2003, who first formalized it as an optimization problem on static graphs. During 2010s, many researchers improved algorithmic efficiency, developing greedy, probabilistic, and heuristic methods. However, they still assume that networks don't change. Recently, as social and communication systems became more dynamic, research shifted towards time aware and adaptive methods. This 2024 paper is one of the first to systematically review and compare all those temporal paradigms. With that background, let's formally define what the influence maximization problem actually is. So, the classical influence maximization problem asks the question: given a graph and a budget of k nodes, which node should we activate to maximize the spread of influence? The expected influence spread is denoted by sigma of S, and finding the best seed set S is NP hard. In temporal networks, it becomes even harder because both edges and nodes evolve over time. Influence can appear, decay, or shift as the structure changes. So the authors focus on understanding how temporal variation affects sigma of S and on evaluating the effectiveness of different seeding strategies. Before exploring those strategies, let's first revisit how influence actually propagates through a network. Every influence maximization algorithm relies on a diffusion model, a rule describing how influence spreads. The paper reviews three major ones, which are independent cascade, linear threshold, and susceptible infected recovered, which is SIR model. So, the independent cascade is where each active node gets one chance to activate its neighbor, whereas linear threshold method is when a node becomes active once the combined influence from its neighbors crosses a threshold. And the susceptible infected recovered SIR model is common in epidemiology, where nodes move from susceptible to infected to recovered. This is a most common used model in a healthcare field. These models form the mathematical foundation for analyzing how ideas, behaviors, or infections spread. Now that the spreading process is clear, the paper next compares how the network structure itself, being static or temporal, changes the outcome. Traditional approaches assume a static structure, where real networks are temporal, which means they change continuously. A temporal network represents this as a sequence of snapshots, each capturing the state at a given time. This matters because the order of connections can dramatically change influence outcomes. If we ignore timing, we might over or underestimate how influence propagates. The authors emphasize that modeling temporal order is essential for accuracy, especially in fast changing systems like online platforms or mobility networks. Understanding this distinction sets the stage for the paper's main contribution, which is comparing four temporal paradigms. This figure from the paper introduces the four main paradigms of temporal influence maximization. The first is the single seeding. This means that all seeds are activated at once at the very beginning, where time t equal to 0. Then comes the second sequential seeding, where one node per time step is activated, allowing feedback from previous influence, and then the maintenance seeding, where periodical updating of the seed sets happen as the network evolves. And lastly, node probing. This introduces active exploration and selects nodes only to spread influence, but to learn not only to spread influence, but to learn hidden network regions. These paradigms gradually move from static to highly adaptive approaches, each balancing realism against complexity. Here, seed means the influential nodes that they use to activate the network. So now let's look more closely at how the single seeding strategies work, starting with the classical greedy method. In the single seeding framework, all influential nodes are chosen right at the start. The best known method is the greedy algorithm, which adds one node at a time based on the largest marginal gain in influence. It's accurate thanks to the submodularity, but it's extremely expensive computationally. In temporal networks, submodularity doesn't always hold, so greedy algorithms lose their theoretical guarantee. As this figure from the paper shows, influence increases sharply at first, then saturates over time. Because this computational bottleneck, researchers looked for faster because of this computational bottleneck, researchers looked for faster probabilistic alternatives, which brings us to the probability based methods. To reduce computational cost, researchers designed probability based algorithms. These methods estimate the expected influence using pre computed probabilities instead of running repeated Monte Carlo simulations. As shown in the line graph, their accuracy remains close to that of the greedy algorithms, around 95%, while the runtime drops dramatically. Such methods make large scale temporal modeling much more practical. In short, they achieve an excellent balance between accuracy and scalability, which is essential when networks evolve in real time. However, even these approaches can still be computationally heavy, which leads us to explore lighter node ranking heuristics. Node ranking methods assign each node as an influence score based on structural metrics such as degree, betweenness, or entropy, and then simply select the top k nodes with the highest scores. These approaches assume that nodes with high connectivity or central positions are most likely to influence others. They are lightning fast and scale easily to millions of nodes, making them very practical for massive datasets like social media networks. However, they are heuristic in nature. They don't incorporate feedback or temporal information, and they assume that the network structure remains constant. As a result, while they perform well in static networks, their effectiveness often drops in temporal settings where connections form and fade continuously. Despite that limitation, they are widely used as a baseline because of their speed and simplicity. This trade off between speed and adaptivity motivates the next stage of research, which is comparing all single seeding approaches side by side and exploring more adaptive paradigms for dynamic networks. Let's now see how the paper summarizes and contrasts these single seeding methods. The table here neatly compares greedy, probabilistic, and node ranking methods, where greedy method gives the highest accuracy but is the slowest, whereas probabilistic approach is almost as accurate but far faster than greedy method, and the ranking method trades some accuracy for huge speed gains. This trade off highlights why researchers began exploring adaptive paradigms like sequential and maintenance seeding approaches that respond to the network's evolution instead of assuming it's fixed. So, next, let's look at how the authors describe sequential seeding. Sequential seeding introduces feedback and adaptivity. Rather than choosing all seeds at the start, we pick one node per step, observe the results, and then decide the next seed. This figure from the paper illustrates that the process where nodes are activated progressively over time. Sequential seeding reacts to the real time influence spread and unexpected network changes. Though slower, it usually achieves a higher final influence in dynamic networks. Building on that idea, the authors next examined two even more adaptive techniques, which are maintenance seeding and node probing. Here the focus shifts toward long-term adaptability, which moves beyond one-time seeding selection to strategies that evolve with the network itself. Maintenance seeding periodically revises or replaces the seed set as the network structure changes. Think of it like refreshing your influencer list regularly to reflect new connections, communities, or behavioral shifts. This ensures that the campaign stays aligned with the latest network topology rather than relying on outdated influence patterns. It's particularly useful in settings where user activity changes rapidly, such as social media, online communities, or mobility networks. On the other hand, node probing tackles a different challenge by dealing with incomplete or partially observed networks. In many real applications, we don't have full visibility into all edges. For example, when a data is missing or privacy restrictions limit access. Node probing dedicates a part of the seed budget to actively explore those unseen areas, identifying new influential nodes and learning unknown links. This exploration exploitation trade off improves model accuracy over time by combining influence spread with information discovery. Together, these two paradigms make influence maximization both adaptive and exploratory, addressing two real world issues simultaneously, which are change and uncertainty. They mark a shift from purely predictive models to ones that can learn and evolve as a network does. Now that we've covered these more advanced paradigms, the paper transitions into a real validation example demonstrating how these ideas perform outside simulation. To demonstrate practical relevance, the authors discuss an HIV awareness campaign among homeless youth in Los Angeles. Influence maximization models were used to select peer leaders who could spread information about safe practices. Here, sequential and maintenance seeding outperformed static approaches because they could adjust as participants joined or dropped out. This case proves that temporal influence maximization isn't just theoretical, but it has real social impact, especially in public health communication. After validating the approach, the authors then synthesize their key insights and future directions. Across all studies, four major insights emerge. First, the static algorithms fail to capture the reality of changing networks, making real world validations still in doubt. Second, integrating graph neural networks allows seed selection to become data driven and context aware. Third, predictive or ex ante modeling could forecast future edges even before they appear. And fourth, adaptive and learning based methods perform better overall, which comes from exploring influence maximization. The authors also highlight the growing importance of influence maximization by reducing misinformation as a parallel research direction. Now that we've seen the findings, let's pause for a moment of critical reflection. While the paper is very strong and comprehensive, it also acknowledges several important limitations. First, it assumes that temporal snapshots are discrete and fully observed, but in reality, network data often arrives as a continuous stream, and many real world edges remain hidden or unrecorded. Handling such incomplete or streaming temporal data would require new online learning techniques that this paper does not yet address. Second, scalability remains a challenge. As networks grow to millions of nodes and edges, even approximate or probabilistic approaches can become computationally intensive. Future work could focus on combining influence maximization frameworks with distributed computing or graph neural networks to improve scalability and responsiveness. Third, while the paper provides a strong comparative framework, it does not include extensive quantitative benchmarks or unified data sets, making direct performance comparisons sometimes difficult. Still, despite these limitations, the framework itself is extremely valuable. It helps clarify how feedback, timing, and uncertainty interact in temporal influence spread, and it provides a conceptual foundation for future adaptive models. So, overall, this study succeeds in balancing theoretical rigor with practical insight, and it opens up multiple promising research directions for the field. Next, the authors encourage us to think deeper, raising a few open questions for discussion. There are three main questions worth pondering. First, which diffusion model truly captures human behavior online? Do people act like the independent cascade or linear threshold model predicts? Second, how can we verify influence in networks that are only partially observed? And third, should we perhaps focus equally on influence minimization, controlling misinformation rather than maximizing the spread? These questions show that network science is not just technical, it is deeply connected to social and ethical dimensions. As we approach the end, let's summarize this paper contributes overall. What this paper contributes overall. Overall, this paper extends influence maximization theory into the temporal domain where networks are dynamic, uncertain, and adaptive. By comparing single sequential maintenance and probing paradigms, the authors show that adaptivity and feedback yield better long term influence. Their framework bridges theory and practice, creating a foundation for intelligent time aware influence modeling. In short, this study reshapes how we understand influence, not as a static event but as an evolving process that mirrors real social systems. I've added the paper's citation. And last but not least, thank you for listening. Through this presentation, we explored how influence spreads not just through connections but through time. The paper highlights that influence maximization is no longer static optimization problem. It's an adaptive, temporal, and learning-driven process. I hope this talk offered insights into both the technical and practical significance of temporal networks. Thank you.